Hey, what's up? This is Tom Thompson from the University of Würzburg at the Space Technology Network podcast. Today we're going to have a look at space radiation and the effects on these guys in orbit, so stay tuned. Okay, let's talk about the space environment which is present at the low Earth orbits or other orbits which we are talking about today. Well, obviously there are lots of sources where the radiation comes from. But there's one source which is really big and which everybody knows about. So let's have a look at this one first and then we'll look at the other ones.
Solar particle events are injections of energetic electrons, protons, alpha particles, and heavier particles into interplanetary space. These particles are accelerated to near relativistic speeds by the interplanetary shock waves, which precede fast coronal mass ejections, and which exists in the vicinity of solar flare sites. The most energetic particles arrive at Earth within tens of minutes of the event of the Sun, while the lower energy population arrives over the course of a day. They temporarily enhance the radiation in interplanetary space around the magnetosphere, and they may penetrate to low altitudes in the polar regions. Satellites in the Earth orbit are therefore affected as well. The Sun's activity is characterized by an 11-year cycle that can be divided into 4 inactive years, which is the solar minimum, and the 7 active years, which is the solar maximum. Changes in electromagnetic radiation, particles, and magnetic fields arriving from the Sun have a significant influence on the space surrounding the Earth. Events such as a solar flare, a coronal mass ejection, which increases during solar maximum, give rise to solar particle events and geomagnetic storms at the Earth. Other features of the Sun, including sunspots, coronal holes, and prominences, are also contributing to the overall dynamic of the Sun-Earth interaction. Some of the most dramatic space weather effects occur in association with coronal mass ejections, which are also called CMEs. These are huge bubbles of plasma, threaded with magnetic field lines that are ejected from the Sun's corona. A large CME can contain 1 billion tons of matter that can be accelerated to several million miles per hour. CMEs are often associated with solar flares and prominence eruptions, but they can occur in the absence of either of these processes. Near solar maximum, the Sun produces about 3 CMEs per day, whereas near solar minimum it produces about 1 every 5 days. The faster CMEs have outward speeds and considerably greater than that of the normal solar wind, and they produce large shock waves in the solar wind as they blow through it. Some of the solar wind ions are accelerated by shockwave, and they become a source of intense and long-lasting energetic particle enhancements in interplanetary space. The movement of the shock waves associated with CMEs and solar flares can give rise to magnetic storms, which are triggered by the collision of fast-flowing particles from the Sun with the magnetic field surrounding the Earth. Depending on the conditions, such collisions inject current called a ring current that circulates around the Earth. The magnetic field generated by the ring current perturbs the Earth's main magnetic field, allowing particles to reach previously unattainable altitudes and inclinations. Such storms are accompanied by enhanced displays, for example of the northern lights. The Earth is surrounded by a magnetic field that looks something like the field you see around a bar magnet. The Earth's magnetic field helps protect us from space radiation such as these solar flares and also the galactic cosmic rays by deflecting many of the particles before they reach us. This magnetic field also traps charged particles within it like an invisible magnetic prison. The trapped particles are so numerous that they form into donut-shaped clouds with the Earth at the center and stretch thousands of miles above the Earth's surface at the equator. Scientists call these the Van Allen radiation belts.
Of course, the Sun is not the only radiation source in space. Other events like supernova explosions, where big stars erupting, well, You can really imagine that these kind of events produce lots of cosmic rays, which then hits the satellite. Also, the cosmic background radiation is always present, and that's not good. We'll see why. Okay, and now that we had a look at the sources of radiation in space, we're going to talk about the effects. And first we start with some basic theory.
Linear energy transfer is a measurement of absorbed power in a material. It can also be understood as some kind of breaking power which is absorbed. It's measured in mega electron volts per cubic centimeter per second, and it's a short-term effect. It's important to notice that this kind of effect depends on the material properties. For example, if you have a material which absorbs very high energies, you might use it as a shielding because it takes away the energy of the rays. Energies that affect chips are mostly in the range of about 30 mega electron volts per cubic centimeter up, but it might be up to 100 mega electron volts. The total dose is a measurement of absorbed energy in a given period of time. It can be understood as the energy which is deposited in a material after a time period. It's measured in kilorats, which is 10 joules per kilogram. The total dose is very important for long-term effects because it accounts for the total energy which is accumulated. Often it leads to degradation of material, but we'll come to that later.
Okay, and with this information we're going to have a look at the effects of the transferred energy and the accumulated energy on chips.
The total ionizing dose effects are a typical case of cumulative effects. The ionizing dose is deposited by particles passing through the materials constituting the electronic devices, like mentioned earlier. This happens through the whole time the device is exposed to radiation. The heart of the total ionizing dose effects is the energy deposition in silicon dioxide, because the electron-hole pairs created in this material do not completely recombine in a very short time. In the presence of an electric field in the oxide, a great amount of the pairs do not recombine, and both electrons and holes start to drift in the electric field. Electrons with a much higher mobility can easily leave the oxide. Holes instead can be trapped in defect centers in the oxide. Additionally, this process can create defects at the silicon-oxide interface. The charge buildup and the activation of defects are the two reasons for device degradation introduced by total ionizing dose. These effects will lead to threshold shifts inside of the transistor, so more voltage is needed or less voltage is needed. Leakage current is also introduced, so the power consumption will increase over a period of time. Noise and timing changes are also very concerning factors, and the worst case is a complete failure of the device.
Total ionizing dose effects are effects which are taking place over a long period of time. But there are also effects which happen really quick, and these are called single event effects, and we're gonna talk about these right now.
The effects of ion-induced charge transients on a circuit depends on several factors, including the minimum charge required to switch states. If a charge is collected from the ion strike exceeds the minimum charge, defined as critical charge or energy, then the passage of the ion will upset or otherwise affect the circuit. Note that the critical charge depends on the specific device design and is not always the same. High-energy ions can induce a number of effects on integrated circuits. Not all of these effects are possible in all devices, either because the critical charge for the effect is too high, or because the specific design of the circuit precludes occurrence of these effects. These effects can be subdivided into a few categories. The first category is transient effects, such as single event upset or multiple bit upset effects that change the state of internal storage elements but can be reset to normal operation by a simple series of electrical operations, like turning it off and on again. Another category is potentially catastrophic events, such as single event latch-ups and snapbacks, that may cause destruction unless they are corrected or within a short time after they occur. The last kind of effects are the catastrophic ones. For example, single event hard errors, which cause catastrophic failure of an internal transistor within a complex circuit. Two mechanisms can cause hard errors: microdose deposition within a gate region and gate rupture. So let's first talk about the not so bad events like single event upset. Single event upset occurs in a storage element when the charge collected from a heavy ion interaction exceeds the critical charge required to upset the circuit. The circuit then changes state, and stored information is lost. However, the circuit still functions normally and can be restored to its original operating state by rewriting or reinitializing the circuit. Originally, only heavy ions caused single event upsets. However, as transistors were scaled to smaller dimensions to increase size and complexity, their sensitivity to a single event upset increased sufficiently so that it was possible for protons to induce upset as well. This may increase the upset rate by several orders of magnitude because of larger numbers of protons in solar flares and trapped radiation in belts, like I've mentioned earlier. Integrated circuits fabricated with complementary MOS or CMOS fabrication processes are very widely used in space electronics. These chips inherently include parasitic bipolar junction transistors formed by closely located CMOS structures that under normal conditions form the integrated circuits N-channel and P-channel transistors, like normal transistors. The collector of each parasitic bipolar transistor forms the base of another parasitic device connected in a positive feedback loop. This circuit is equivalent to a 4-layer diode device commonly known as silicon-controlled rectifier. Under normal operation, no current flows through the parasitic base regions. However, if a small current is injected into a base region, perhaps because of the charge collected from a single particle energy position, the positive feedback will cause the current to quickly become very large. The high current will continue to flow between the integrated circuit power supply pins until the voltage drops below a threshold called the holding voltage. This sustained high current state, induced by a single particle interaction, is referred to as single event latch-up. A latch part can be permanently damaged as a result of thermal runaway or failure on-chip metallization or packaged bond wires. However, if power is quickly removed or current is limited, damage to the integrated circuit can be avoided. Not all latch-up events are the same. If power is quickly removed after a latch-up event, the positive feedback is not activated and no damage might be done to the device. Still, it might be stuck in an upset state, meaning it cannot be used properly anymore. This can also happen if the deposited energy is not that high compared to a normal latch-up event. This effect is referred to as micro latch-up. Depending on the position of the upset part, there can be unforeseen effects on the operation of the struck device. There are lots of ways to protect from these events, but we will talk about that more deeply in the next episode. Still, I want to mention some techniques about how to prevent your electronics from malfunctioning or even dying in an ion strike. Shielding is the easiest thing, which can be done without changing the electric circuits as a whole. Different materials are being used, for example thin sheets of aluminum or a material called tantal. Tantal is the preferred one because it has a very certain molecular structure and is also very dense. This prevents ions or rays from depositing their deadly dose to the circuits itself. But one has to be careful. Sometimes certain effects happen only at the very distinct energies. That means that, for example, an ion enters a chip, the energy might be dissipated through the shielding, so the remaining energy will be exactly that energy needed for a single event upset, for example. That means that lots of tests have to be done beforehand. Also, mass and size of a chip must be considered when applying shielding. I already mentioned a very elegant way of preventing a latch-up. By sensing the current inside a CMOS chip, one can prevent transistors from burning up by removing the power in the event of a current spike induced by cosmic rays. Therefore, the positive power feedback loop cannot damage the chip because there is no feeding. But that also means complicated integration of such circuits. Because all the mentioned events happen on a space mission, and also the best protection might not prevent any chip from being destroyed or degenerated, it is very common in spaceflight that you add redundancy to your components. Sensors, for example, are therefore multiplicated, so that in the event of a failure of one device, there are still other devices which may carry the same operations. Other ways will be discussed in another episode.
As you can see, there's lots of things to consider if you're doing a spacecraft mission. Keeping in mind that the environment in space is very hostile and you have to do protection against it will ensure your mission will succeed. But still, there are other hazards to spacecraft. We'll talk about that in another episode. Till then, this is Tom Thompson from the Space Radio Network. See you soon.